Russ called and he said, there's something wrong with your product. There's something weird here. We're going to have to test it again. Can you send us some other samples? So we said, sure. And at that point, we began to think, this is going to be an interesting study because they're already talking about things that they'd never seen before. So this is what you're looking at. On the left, you're looking at an 8-ounce glass of deionized water. This is a pure, it's actually reverse osmosis deionized water, almost a dead water. It has virtually no nutritional content to it. And I'm going to bring your attention to this middle area first before we get into some of the actual measurements. Oops, let's go back here. This middle area here, you're looking at basically the glass of water, and you're looking at a very, very unstable environment. This is very rare for water, especially for distilled water, but that shows you how accurate their testing equipment is. On the right, this is the same glass of water after they've added 8 drops of Cellfood. You can see how much more stable environment Cellfood provides. So let's get into the testing. The first testing that they did was they actually wanted to measure something called conductivity. And conductivity is basically what we call electrolytes. Anybody heard of Gatorade? Huge seller of electrolyte potential or electrolyte concentrate. Well, that's what we're talking about. We're talking about extracellular and intracellular communication inside the human body, and it's called conductivity. Well, the glass of water measures 9 microsiemens, which is relatively flat. 0 microsiemens would be flat, but at 9, they're measuring at least a little bit of conductivity. This is Cellfood. 192,323 microsiemens. This is about the equivalent of 40 bottles of Gatorade in 8 drops of Cellfood. Extremely, extremely potent electrolyte. So the next study we asked them to do was to actually measure the mean zeta potential. Mean zeta potential, again, is measuring the actual microconductivity of the water itself, and it measures the ionization. If it's positively charged, that means that, to explain it, it's kind of like water and oil. Water and oil are not able to penetrate each other because of their surface tensions don't match. Well, if you have a positively charged ionic formula into a negatively charged ionic formula, it's not going to mesh. It's not going to allow any permeation. So we measured the glass of water, and it measured, as we thought, a positive 3.65. Cellfood measured a negative 22.66 millivolts, which is virtually identical to the intra and extracellular fluids inside the human body. That's one of the ways that we're able to get such great absorption and assimilation of the nutrient content. Furthering this idea of surface tension and how is it that water and oil, or why is it that water and oil are not able to penetrate each other, when you put Cellfood into a glass of water, a lot of people talk about water being a wonderful hydration molecule, and it actually is. It measures very, very well. But it measures very well despite the fact that water has a much higher surface tension than the extracellular and intracellular cells that are inside the human body. Despite that fact, water is still a great hydration tool. But how much better is it with Cellfood? Well, we decided to measure. What you're looking at here is a chart that was done by Augustine Scientific Laboratories, and it actually measures the water at the very beginning, which is here, at 70 microdynes. This is what regular water is. Extracellular body fluids are down here around 40 to 45. As soon as we put in Cellfood into 8 drops of Cellfood into 8 ounces of water, we saw a dramatic decrease in surface tension down to the exact same surface tension of extracellular and intracellular body fuels. And here's the second part of the study, the exact same thing. Both results showed that Cellfood was able to decrease the surface tension of that glass of water to increase the absorption and the hydration of the human body.